Hello friends, welcome back to a new session of MOOC on Information Security, Public Key Cryptography. Public key cryptography or asymmetric cryptography is an encryption scheme that uses two mathematically related but not identical keys, a public key and a private key. Unlike symmetric key algorithms that rely on one key to both encrypt and decrypt, each key performs a unique function. The public key is used to encrypt and the private key is used to decrypt. It is computationally infeasible to compute the private key based on the public key. Because of this, public keys can be freely shared, allowing users an easy and convenient method for encrypting content and verifying digital signatures, and private keys can be kept secret and ensuring only the owners of the private keys can decrypt content and create digital signatures. Since public keys need to be shared but are too big to be easily remembered, they are stored on digital certificates for secure transport and sharing. Since private keys are not shared, they are simply stored in the software or operating system you use or on hardware, example USB token, hardware security module, etc., containing drivers that allow it to be used with your software or operating system. Characteristics of public encryption key. Public key encryption is important because it is infeasible to determine the decryption key given only the knowledge of the cryptographic algorithm and encryption key. Either of the two keys, public and private key, can be used for encryption with another key used for decryption. Due to public key crypto system, public keys can be freely shared, allowing users an easy and convenient method for encrypting content and verifying digital signatures, and private keys can be kept secret, ensuring only the owners of the private keys can decrypt content and create digital signatures. The most widely used public key crypto system is RSA, reversed Shame-Adelsman. The difficulty of finding the prime factors of a composite number is the backbone of RSA. For example, public keys of every user are present in the public key register. If B wants to send a confidential message to C, then B encrypts the message using C's public key. When C receives the message from B, then C can decrypt it using its own private key. No other recipient other than C can decrypt the message because only C knows C's private key. The keys generated in public key cryptography are too large, including 512 bits, 1024 bits, or 2048 bits, and so on. These keys are not simply to learn. Thus, they are maintained in the devices, including USB tokens or hardware security modules. The major issue in public key crypto system is that an attacker can masquerade as a legal user. It can substitute the public key with a fake key in the public directory. Moreover, it can intercept the connection or alters those keys. Public key cryptography plays an essential role in online payment services and e-commerce, etc. These online services are ensured only when the authenticity of public key and signature of the user are ensured. The asymmetric crypto system should manage the security services including confidentiality, authentication, integrity, and non-repudiation. The public key should support the security services including non-repudiation and authentication. The security services of confidentiality and integrity considered as an element of encryption process completed by private key of the user. Basic principles of public key crypto systems. The concept of public key cryptography evolved from an attempt to attack two of the most difficult problems associated with symmetric encryption. Key distribution under symmetric encryption requires either that two communicants already share a key which somehow has been distributed to them, or the use of a key distribution sender. Whitefield Diffie, one of the discoverers of public key encryption, along with Martin Hellman, both at Stanford University at the time, reasoned that this second requirement negated the very essence of cryptography, the ability to maintain total secrecy over your own communication. The second problem that Diffie pondered, and one that was apparently unrelated to the first, was that of digital signatures. If the use of cryptography was to become widespread, not just in military situations but for commercial and private purposes, then electronic messages and documents would need the equivalent of signatures used in paper documents. A public key encryption scheme has the following ingredients, which are as follows. Plain text. This is the readable message or information that is informed into the algorithm as input. Encryption algorithm. The encryption algorithm performs several conversions on the plain text. Public and private keys. This is a set of keys that have been selected so that if one can be used for encryption and the other can be used for decryption. Ciphertext. This is scrambled message generated as output. It is based on the plain text and the key. For a given message, there are two specific keys will create two different ciphertext. Decryption algorithm. This algorithm gets the ciphertext and the matching key and create the original plain text. The essential steps are the following. Each user generates a pair of keys to be used for the encryption and decryption of messages. Each user places one of the two keys in a public register or other accessible file. This is the public key. The companion key is kept private. Each user maintains a collection of public keys obtained from others. If Bob wishes to send a confidential message to Alice, Bob encrypts the message using Alice's public key. When Alice receives the message, she decrypts it using her private key. No other recipient can decrypt the message because only Alice knows Alice's private key. With this approach, all participants have access to public keys and private keys are generated locally by each participant and therefore need never be distributed. As long as a user's private key remains protected and secret, incoming communication is secure. At any time, a system can change its private key and publish the companion public key to replace its old public key. Invariably, the private key is kept secret, but it is referred to as a private key rather than a secret key to avoid confusion with symmetric encryption. This figure shows how you can freely distribute the public key so that only you, the owner of the private key, can read data that was encrypted with the public key. In general, to send encrypted data to someone, you must encrypt the data with that person's public key, and the person receiving the data decrypts it with the corresponding private key. If you compare symmetric key encryption with public key encryption, you will find that public key encryption requires more calculations. Therefore, public key encryption is not always appropriate for large amounts of data. However, it is possible to use public key encryption to send a symmetric key, which you can then use to encrypt additional data. The reverse of what is shown in the previous figure also works. That is, data encrypted with your private key can be decrypted only with your public key. However, this is not a desirable way to encrypt sensitive data because it means that anyone with your public key, which is by definition published, could decrypt the sensitive data. Despite this, private key encryption is useful because it enables you to use your private key to sign data with your digital signature. Anyone with your public key can be assured that only you send the data. This is an important requirement for electronic commerce and other commercial applications of cryptography. Let's take a closer look at the essential elements of a public key encryption scheme. Using this figure, there is some source A that produces a message in plain text x equal to x1, x2, etc. xm. The m elements of x are letters in some finite alphabet. The message is intended for destination B. B generates a related pair of keys, a public key PUB and a private key PRB. PRB is known only to B, whereas PUB is publicly available and therefore accessible by A. With the message X and the encryption key PUB as input, A forms the ciphertext y equal to y1, y2, etc. yn with the equation y equal to E of PUB x. The intended receiver in possession of the matching private key is able to invert the transformation x equal to D of PRB y. An adversary observing y and having access to PUB but not having access to PRB or x must attempt to recover x and or PRB. It is assumed that the adversary does have knowledge of the encryption E and decryption D algorithms. If the adversary is intended only in this particular message, then the focus of effort is to recover x by generating a plain text estimate. Often, however, the adversary is interested in being able to read future messages as well, in which case an attempt is made to recover PRB by generating an estimate. We mentioned earlier that either of the two related keys can be used for encryption, with the other being used for decryption. This enables a rather different cryptographic scheme to be implemented, whereas the scheme illustrated in the second figure provides confidentiality and figure 3 show the use of public key encryption to provide authentication. Y equal to E of PRAX and y equal to E of PUAY. In this case, A prepares a message to B and encrypts it using A's private key before transmitting it. B can decrypt the message using A's public key. Because the message was encrypted using A's private key, only A could have prepared the message. Therefore, the entire encrypted message serves as a digital signature. In addition, it is impossible to alter the message without access to A's private key. So, the message is authenticated both in terms of source and in terms of data integrity. In the preceding scheme, the entire message is encrypted, which although validating both author and contents requires a great deal of storage. Each document must be kept in plain text to be used for practical purposes. A copy also must be stored in ciphertext so that the origin and contents can be verified in case of a dispute. A more efficient way of achieving the same results is to encrypt a small block of bits that is a function of the document. Such a block, called an authenticator, must have the property that it is infeasible to change the document without changing the authenticator. If the authenticator is encrypted with the sender's private key, it serves as a signature that verifies origin, content, and sequencing. It is, however, possible to provide both the authentication function and confidentiality by a double use of the public key scheme. Z equal to E of PUB and E of PRBX and X equal to D of PUA E of PRB set. In this case, we begin as before by encrypting a message using the sender's private key. This provides the digital signature. Next, we encrypt again using the receiver's public key. The final ciphertext can be decrypted only by the intended receiver, who alone has the matching private key. Thus, confidentiality is provided. The disadvantage of this approach is that the public key algorithm, which is complex, must be exercised 4 times rather than 2 in each communication. Public key cryptosystem uses. In public key cryptography, every user has to generate a pair of keys among which one is kept secret known as private key and the other is made public, hence called as the public key. Now, the decision of whether the sender's private key or receiver's public key will be used to encrypt the original message depends totally on application. The use of public key crypto system is defined into three elements which are as follows. First one is encryption or decryption. If the purpose of an application is to encrypt and decrypt the message, then the sender has to encrypt the message using the intended receiver's public and the receiver can decrypt the message using his own private key. Second one is digital signature. If the purpose of the application is to authenticate the user, then the message is signed or encrypted using the sender's private key. As only the sender can have its private key, it assures all parties that the message is sent by the particular person. And the next one is key exchange. The two communicating parties exchange a secret key, maybe a private key, for symmetric encryption to secure a particular transaction. This secret key is valid for a short period. Requirements for a public key crypto systems. The crypto system illustrated in figures 2 through figure 4 depends on a cryptographic algorithm based on two related keys. Diffie and Hellman postulated this system without demonstrating that such algorithms exist. However, they did lay out the conditions that such algorithms must fulfill. It is computationally easy for a party B to generate a pair public key a PUB, private key PRB. It is computationally easy for a sender A knowing the public key and the message to be encrypted M to generate the corresponding ciphertext, which is C equal to E of PUB M. It is computationally easy for the receiver B to decrypt the resulting ciphertext using the private key to recover the original message. M equal to D of PRBC, which is equal to D of PRB E of PUB M. It is computationally infeasible for an adversary knowing the public key PUB to determine the private key PRB. It is computationally infeasible for an adversary knowing the public key PUB and the ciphertext C to recover the original message M. We can add a sixth requirement that, although useful, is not necessary for all public key applications. The two key can be applied in either order. M equal to D of PUB E of PRB M, which is equal to D of PRB and E of PUB M. These are formidable requirements as evidenced by the fact that only a few algorithms RSA, elliptic curve cryptography, Diffie-Hellman, DSS have received widespread acceptance in the several decades since the concept of public key cryptography was proposed. So, in this session, we had discussed the important properties, requirements and uses of a public key crypto system. We will see again with different algorithms used such as RSA in the coming sessions. Hope you understand this session. See you next time. Bye.